this is work that I did with quite a few people over quite a few years, and very mostly here. Okay, so my former students, which are actually and student I collaborate with, Jing Shua, are at the bottom, and my senior collaborators are at the top, and also the late Ken Kelton is there as well. Okay, so as you might know in general, especially those of you in condensed matter, but also many of you are not in condensed matter, one of the ways people thought of, one of the original motivations for thinking about atoms, there were many motivations people thought, also Democritus thought about atoms, but one of the motivations people thought about atoms and the underlying atomic structure and the regular structure was looking at crystals. So if you have nice crystals, like the one that you see here and so on, then the very existence of very sharp facets that you see hints that maybe the underlying macroscopic structure is of that type. And basically that structure gets replicated many, many times over, and it appears in macroscopic scale. So the existence of nice facets of crystals was a very, very strong hint that maybe there's atomic structure, which by virtue of being periodic, reproduces and gives rise to what we see on the large scale. And of course, this is not only for understanding the structure as we know nowadays, but also for thinking about electronic properties and so on, where we have atomic levels in single atoms can appear over an entire system, macroscopic system involving many, many atoms, by virtue of the system actually becoming periodic. But of course, life is richer than periodic systems. Even though we love periodic systems, when we teach our students periodic systems, and there are many powerful things we can do with periodic systems, there are many systems around us, particularly most things around us, are not necessarily ideal crystals. So one of the things we want to think about is what happens for systems which are amorphous, in particular, what happens to glasses, okay, and supercooled fluids in general. And again, this is a very, very old question. This is an old field, and there are many different ideas people had over the years, sometimes overlapping ideas. One of the conjectures people had by now 70 years ago was to think about what would structure would be naturally if you supercool a system. What does supercooling mean? Supercooling means that you take a system at high temperatures, let's say a fluid. If you were to cool it down slowly enough, usually, it will become a solid, a crystal. Not always, of course, there are outliers. We all know about helium and so on and atmospheric pressure. But usually, if you do it right and you do it slowly enough, then it becomes a crystal, okay? But suppose that you cool it down so quickly that it doesn't get a chance to crystallize. You can then ask, what happens in that situation? So I don't have necessarily sharp facets of the crystal that I see because there's no long-range order that appears in that system whatsoever. But still, deep underneath, what structures would I see if I could peer underneath, describing the macroscopic realm? And so an idea that people had, okay, this is a cartoon of Frank, was basically that you want to minimize interactions as much as you can locally. So basically, if you supercool a system if you cool a system very, very rapidly, the system doesn't have enough time to calculate all possible configurations. It tries to minimize quickly what the right answer might be, okay? So quickly, if you just force yourself to guess what configurations might naturally occur, you basically evolve under the influence of forces and so on. Quickly, what might happen is that you veer towards minima, local minima, that corresponds to packings that you would have that have low energies. And for instance, one natural structure is that of an icosahedron. So basically, you want to pack as many atoms together closely as possible to minimize interaction energies. And locally, if you do that, you can have things that look like an icosahedron. Of course, as you know very well, you cannot pack icosahedra together completely to tile space. That's why we typically have regular crystals and not icosahedral ones. But nonetheless, locally, this is what you would have gotten, okay? And indeed, you can do experiments that are done by my late colleague, Ken Kelton, and you can indeed, and others since, and you can indeed see X-ray measurements that confirm that you can really see that they agree precisely what was predicted by Frank many, many decades ago. This was on the cover of Physics Today some time ago, and I actually read this paper, I mean, shortly before I joined, sometime before I joined, well, actually not very long. This is actually one of the draws I had for actually coming there. So this is a comparison between the energy that you have for this icosahedral structure. I apologize about that. Icosahedral structure, okay? And this E icosahedral means energy of icosahedral cluster, as compared to a regular crystal, which is a phase-centered cubic crystal. Okay, so the icosahedral cluster locally has lower energy than the regular lattice. That's why the system might prefer, if quenched, to veer towards those configurations. Okay, the difference is not large. So relative energy difference is of the order of 8% or so. Okay, but nonetheless, it's non-negligible. And this is what the system might actually want to do. And indeed, in metallic glasses, you see precisely these sort of motifs, because the interactions are described by interactions of this type, to do an approximation. And this is what my late colleague actually found. So this is a cartoon of why we might expect to find icosahedral structures. Okay, so let's imagine we have a Lennard-Jones interaction. So I assume you all know what the Lennard-Jones interaction is. You have an interaction between atoms. The interaction has a minimum at a particular value of separation. Of course, it's not only Lennard-Jones. Many potentials have this type. There's a well-defined minimum where atoms want to be at the distance from each other, which is fixed. And then if you go to larger and larger distances, of course, then that interaction energy goes to 0. And there's a hardcore interaction. So at very, very short distances, the system is repulsive. V of R diverges, becomes very large. There's a minimum that appears, definite value, which here is labeled R minimum. And then at asymptotically large values of separation, the interaction goes to value of 0. So suppose I have two atoms, and I want to minimize the energy, the potential energy of these two atoms, given this interaction profile that you see there, V of R. Okay, so you have this interaction profile. You want to minimize the configuration that you have. So clearly, if you have two atoms, the best that you can do is to put them apart a distance of R minimum. So this interaction V of R is precisely minimal. That's a piece of cake. What happens if you have three atoms? Well, you can generalize this. You can put basically all of them at the vertices of an equilateral triangle. Okay, this equilateral triangle here. And again, all these distances are the same. All pair interaction minimize the value V of R. And you couldn't do better than that. So if you want to minimize interactions locally, this is what you would get. And this motif here, this triangle, can actually tile an entire lattice. You can have triangular lattices or hexagonal lattices. Okay, so indeed, you can actually have these structures appearing quite naturally and also globally. What happens if we go to 4 atoms? If we go to 4 atoms, then you would form this tetrahedron that you see here, or you saw here a few seconds ago. Sorry about this. Okay, this one that you see here at the bottom left corner, I apologize. Sorry about this. This one that you see here at the bottom left, okay? So this minimizes, again, all pair interactions, okay? Now we have 4 atoms, we have 6 pairs, and all of them are happy because they minimize the interactions. What happens if we go beyond 5, okay? So then at some stage, as you can see, we have problems because, as you might know, the opening angle of a tetrahedron is not a fraction, a nice fraction of 360 degrees. Okay, it's almost there, but not quite. So you cannot actually tessellate space completely with these tetrahedra. You can form a icosahedron, which is slightly distorted, and you can generate these motifs, which Frank was thinking about a very, very long time ago. Okay, and you can have these motifs appearing and so on, and maybe on a larger scale with some contortions and so on. But this is what you might have locally, but certainly not globally, because it's not consistent with the geometry of flat space. You can do it in curved space. People have thought about that a long time ago, but not in flat space, not degree space. So now let me tell you, if I run out of time, what the conclusions are of my talk. And then you can decide if you want to follow it or do other stuff. Okay, so basically, I'm going to think about probability distributions describing supercooled fluids inspired by thinking about low energy structures and more generally by considerations of quantum mechanics and physical mechanics. And what I will think about are distributions of effective state variables. So temperatures, chemical potentials, things like that. So my thesis is essentially that if you have long-lived structures like what we find in supercooled fluids, so ultimately supercooled fluids would crystallize if you wait long enough, okay? But it takes a really long time on the microscopic scale. So these such states, if they were completely stationary, okay, then basically they would be described by distributions of state variables, what we have in equilibrium. So basically, I want to think about what happens if we have not a probability distribution describing system of sharp state variables, which we teach our students zero-flow dynamics and things like that and so on. Of course, conventionally, we always have sharp state variables. But what happens if we have a mixture of state variables? Can it arise naturally? I will argue that yes. I'll also argue that actually must occur by proving a simple theorem, but with assumptions is infinitely long-lived, okay? And then I'll not only try to think about that, because of course, life is not about theorems of idealizations and so on. Life is about real data and real calculations that you have for real messy systems, and which are not necessarily solvable so readily. So I'll try to compare this to real data and ask myself, can you really understand supercooled fluids and liquids, supercooled liquids and gases described by such a mixture of temperatures of equilibrium systems, equilibrium fluids and solids? Does that actually give predictions that are consistent, or is it consistent more precisely, with what the data, experimental data actually show? It's consistent. It doesn't prove anything. It proves that it's not inconsistent. It doesn't mean it's right, okay? It just proves it's not inconsistent, and hopefully it's correct, but of course, that's in the eye of the beholder. But these are sort of interesting questions in general. What can we think about situations where we have a mixture of state variables? It's a general question. People thought about this in plasmas and elsewhere, and also in other systems, which I just learned about today. But can this describe actually supercooled fluids and give rise to predictions that you can actually measure? Okay, so that's the answer to that, I think, is yes, in the sense of being consistent. So what's shown here is a collapse of data, okay? So this was compiled by my former student, Nick Weingartner. So here are just raw data. You cannot read it so easily, I apologize. There's lots of fluids here. Overall, there are 66 different systems that are shown here. And here, basically, there's only one parameter per fluid. So basically, just raw values with one-dimensional number, which is nearly constant per fluid. So what's plotted here? On the vertical axis, what we plot is the logarithm of a viscosity, eta, at temperature T. So the viscosity essentially monitors, not exactly a proxy of that, but it monitors essentially relaxation times, so-called alpha relaxation times, okay, people with different names and so on, of a system, the long relaxation times of the system, divided by the viscosity at temperature T, divided by the viscosity that you have in the at equilibrium melting, which is this is L, not, this is liquidus, not 1. The viscosity eta at T sub L, T liquidus, in equilibrium, okay? So you see, I have it for viscosity. I also have it for tau. Tau is relaxation times that you can extract from dielectric response measurements, AC dielectric response measurements. Again, scaled by what you have for equilibrium system at temperature TL, over the system itself, before at temperature TL. So this is just pure data, no dimension, no fitting here whatsoever, okay? No parameters here. This is dimensionless, and of course, as you see here, as it always is for many people, everybody that investigates supercooled fluids, usually we have to plot things on a log scale because relaxation times and viscosities and so on, they can shoot up by many orders of magnitude, especially for so-called fragile fluid, by many, many orders of magnitude. So you see here on the vertical axis, this changes by 16 decades. So this is, of course, all data that we had. But the point is, individual fluids can actually also, especially so-called fragile ones, have a change in their time scale, in their dynamics, which can be astronomical, okay? Which is a puzzle in general. How can it be? Usually we think about critical slowing down, things like that. Things can slow down, but they don't scale in a way which is so dramatic as we see here, especially without the concomitant transition but with associative long-range orders that we think about. Okay, so here on the x-axis, plot x here, is basically just the, again, raw values. So this is T melting, T liquidus, minus temperature itself, divide by temperature. So this is like a reduced temperature, but not quite. Instead of dividing by the critical temperature, or more precisely, the liquidus temperature, here we divide by temperature itself. This is like a conformal thing, if you want. The natural scale of a problem is temperature itself. There's a square root of 2 because that came about because when I originally derived it, I had a square root of 2 there. That's not terribly important. There is a parameter there, this A bar. Okay, you see this A bar. Each individual fluid has one number, A bar, which was adjusted to make this collapse onto one curve. This value of A bar is nearly constant across all of these different fluids. Nearly, they're outliers. And for some of them, as you can see here, it doesn't work very well. So you see here, some fluids don't collapse very well. But by and large, it collapses moderately well, I would say, with only one adjustable parameter. And more important than that, the only natural energy scale, temperature scale in the problem is that of equilibrium. It's that of melting that you would have in equilibrium, not a parameter that people usually think about, like so-called Vogel-Fulcher fates and mode coupling and so on, that people sort of surmise that there's something else going on, which is more complicated. Here we just use equilibrium results. Okay, again, this doesn't prove anything. It just shows that it's consistent. Maybe the origin for this is very different from what I'm about to tell you. Could be the case. But as a matter of principle, you see that regardless, all data collapse into one curve with some outliers, but very few of them. And the collapse does not become worse as you go away from the transition, actually becomes better, as you can see. These are the actual values of these parameters. So these are the different fluids, as you can see here. Again, compiled by my former student, Nick Weingartner. Okay, these are the corresponding values that we had for the liquidus temperatures in Kelvin. Apologize for this. Sorry about this. I apologize. Okay, and this is this parameter, A bar, that I mentioned earlier, okay, on this column. Okay, it fluctuates, you see, 0.06, 0.05, 0.05, 0.07, and so on, but it doesn't change that much. Here it's 0.117, okay? Sometimes, overall, it fluctuates, but it doesn't fluctuate that radically, okay? So it's actually quite constant over these different values of the different fluids. And if you look at the average value that you have of the different fluids, okay, so it comes out around 8.4%, which is not too dissimilar from what you have if you think about energy considerations. I told you about what you would have for aqueous structures as opposed to FCC lattices and so on locally. It gave you the same order of magnitude, actually in this case almost exactly the same thing, okay? But that's a fluke if it's indeed related. What's important is that overall the fluctuations are not that large, and this natural scale A bar can be perhaps ascribed to differences that you have in energies of locally preferred structures that you would have going either locally preferred that you do locally, and of course you also have energetic regions which cost more energy on the other side. Okay, and there are outliers, as I mentioned earlier, and so on. I mean, now you can also do simulations on various many of these systems. Of course, idealized usually, because of course doing it for a real system is quite complicated, but people either look at potentials that give rise to what they actually see, and they're potentials people use all the time, or you can think about other potentials people use more theoretical and so on. But many people invested a lot of time thinking about these. So we use also these so-called Cobb-Anderson type potentials. And we looked at the distribution that we would have for local temperatures. So this is what this T bar represents. So I told you that I'll be thinking about distributions of state variables. This parameter A bar was actually a proxy for telling us about the distribution itself. It was a distribution parameterized by this one single dimensional number, okay? And here we actually did a simulation. We looked at the velocity distributions. We went back and assumed the Maxwell distribution, as of course happens, as we all know, regards the potential for all equilibrium systems. And from that, we extracted what distribution is of effective equilibrium temperatures. And this is what we actually find. Okay, so this is what you actually find. So essentially, it's a gamma, so-called gamma distribution, which many of you probably undoubtedly know. But in the regime that we are looking at, where this value A bar is small, essentially is Gaussian. Okay, and the point is that, as you can see here, this temperature varies in general, of course. It becomes essentially very small, away from where it's peaked, obviously, as you can see that. But importantly, if I think about some value of temperature as being the equilibrium melting temperature, and I would say that above this temperature, I have hydrodynamic flow, and above it and below it in equilibrium, I would have basically no motion whatsoever. I would have basically oscillations, I would have phonons, I would have things of that nature, but I would not have overall displacements, okay? I would not support hydrodynamic flow. And I look at the area that I have of this tail that I have above this cutoff temperature, okay? And I could use this distribution and evaluate that. And from that, see what the prediction is for the viscosity and compare that to what you have when you measure numerically the viscosity, which is easier said than done, because when you go to low temperatures, actually, you have to wait a very, very long amount of time, which we couldn't because it was just taking too long. But what we could do is we can compare that, which is what these dots are, to a real data, okay? And this fit is a conventional one. We don't want it to be biased by our own fit. This is a conventional one, the so-called Vogel-Fulcher-Tammann fit, okay, which is by now over 100 years old, 105 years old, okay? And it actually is consistent with that. So the area of this tail, this distribution that you have, that you can extract from simulations, is consistent. Again, it does not prove anything, but it's consistent with that. Okay, so just to sort of summarize what I want to say before, we're asking, can we have a distribution of state variables? Also was asked by one of you. I didn't know about it until today. Okay, what it gives rise to, can we use it to actually make predictions? And it seems to actually be consistent. Okay, and then I want to ask another question, which was inspired by that question. Can we actually have relations if I think about distributions of state variables and in general, okay? And doing that, we actually arrived at relations which relate to what many of you also involved in string theory know very well, which are these. So as you might know, Damson and many others and Sharon Hartnell and Subir Sachdev and many others were thinking about bounds that you would have, fundamental bounds that you would have for viscosity and other quantities, which relate to fundamental constants of nature. Basically, initially, people were looking at the viscosity to entropy density ratio, relating this to Planck's constant and Boltzmann constant. Okay. Actually, as you know, Planck was actually the one to introduce Boltzmann's constant. Boltzmann didn't actually write down his constant. Planck did. But anyway, that's a separate story. So you can actually get, using these some considerations related to this, you can get bounds, this is what we did, which relate to these conjectures, which are rigorous, okay? And these are quantities we wanted to bound, okay? These are the bounds that we actually get, okay? So these bounds are rigorous. Some of them actually are more approximate. So because the rigorous bounds are not terribly useful, so you want to get something which is simple. And then you can compare that to real data. Okay, so you can compare this to actual real data. I apologize about this. So these are the actual values that you have for different materials, okay, common materials, okay. You can compare it to actual values that you would have for those materials, and you sort of see that in many situations, the disparity is not large. So the bounds are not just a device, even if correct, are not just some useless bounds, but actually are nearly saturated in many situations, especially when you make approximations, make them more simpler, of course. Okay, and if you want to really be more strict and so on, so then you sort of see that there's a big disparity between the actual values. I apologize about this for this. The actual values, like here, okay, the bulk viscosity, but the actual in this column here, and the experimental observed value. The bound is satisfied, but it's quite useless. Okay, but in general, if you make approximations to make it simpler, you can actually get useful bounds. And all of these results basically relate to using open system, sort of hydrogen, thinking about open system quantum mechanics, and basically use uncertainty relations that you would have for open systems. So usually we think about uncertainty relations for pure quantum states that we teach our students and so on, the usual derivation of Heisenberg uncertainty relations and so on. But you can actually extend very readily also for open systems. It's just a few lines. There are many ways of doing it, but all of them are just a few lines. There are more complicated ways of doing it, a few pages, but you can also prove it in just a line or two, okay? And if you do that, you can basically relate the rate of change that you have for local observables, which is what I had here. Sorry about this. Which is what I have here at the bottom right, okay? Bottom right here, to what you have in the quantities involving fundamental constants of nature, basically Planck's constant, Boltzmann constant, temperature itself, and what I call here a local heat capacity. This is C sub Vi, which I'll explain more if I have time. I probably won't have enough time to explain it. Okay, and not only can you actually think about bounds on dynamics, you can also get bounds on gradient. You can actually prove quite readily, okay, that if you look at the general function f in thermal equilibrium, its relative gradients cannot be arbitrarily large in equilibrium. They're actually bounded by fundamental constants as well, okay? And this is basically, in this case, for non-physics systems, it's basically given by the Schrödinger wave that you would have. And again, this is by the use of the uncertainty relations. And all of this basically relates to thinking about distributions that you would have, I apologize for this, that you would have a involving, sorry about this, not sure what happened. So the point is, in general, if you have a driving mechanism, like if you supercool a system or you superheat a system, or you apply a field very, very quickly, or apply pressure, a strain, whatever you want to think about, you do it rapidly. It's not adiabatic, okay? Then in general, what you can actually have is long-range correlations, okay? You can have this distribution of state variables, as I mentioned. I actually explained to you why that's the case. And this also, these considerations, the absence of having this spread of also gives rise to these bounds I flashed for you a few minutes ago. So let me skip this because I don't want to go out of time too quickly. And let me tell you a little bit about the glass problem, so-called the glass problem. This is a quote by Phil Anderson. So many of you, especially those in condensed matter, undoubtedly know very well Philip Anderson's work. And he was, putting his opinion on 30 years ago, over 20 years ago by now. And his opinion at the time, for over 30 years ago, the deepest unsolved problem and so on is basically that of the glass problem. And he thinks it will actually have many implications. And I apologize for this, many implications, and it might actually have relates to spin glasses and may also have maybe a computer algorithm and neural networks and complexity and so on. So thinking about disordered systems, and maybe also have practical benefits, but maybe not. But it actually helps us to make better glasses. Questionable, but regardless, it will actually be very, very important for understanding. Because it's such an important question, there have been lots of theories about this, like in string theory, of course. There's a landscape of theories. So I took this unabashedly from a string theory paper. And of course, there's a swampland, the swamp conjecture, and so on. The same sort of thing can be said also for theories of glasses, for many of them. And undoubtedly, most of them it's probably not possible that all of them are right. Most of them are probably wrong. Where they overlap, probably they're correct. And there's some common themes people have. And usually some camps, some people think about that they're in this camp, and people think in that camp. Different camps feel the other camp is wrong. Okay, so I'm not going to get to sociology right now, but it's a complicated problem in the sense also of sociology apart from physics itself. Okay, so what is the actual problem itself? So as I already mentioned, a supercooled fluid is basically one in which you take the system and you cool it down very, very rapidly, so it bypasses crystallization to the usual equilibrium crystalline state. And this can happen for any system in principle. So usually we think about window glasses and reading glasses that we have and so on. But of course, it's not just that. It's also metallic glasses. Everything in principle can be supercooled, and if at low temperatures, pushing low temperatures, it will become so-called glass. But it can also be electronic glasses. Okay, you can also think about spin systems, anything that you like. Okay, it's believed that in general, if you are able to, it's a big question if you are able to, but if you are able to supercool it, it will become supercooled fluid, and at some stage, if you keep supercooling it, it will become a glass. It's not always possible. As I said earlier, helium cannot be supercooled. It's essentially impossible to supercool it. But as a matter of principle, this is believed to be the case. So here essentially is a cartoon, not a cartoon, an actual experiment you can do of what is going on. So supposing you take a container, you fill it up with water, you put it in the freezer. Of course, we all know what happens if you wait long enough, it becomes solid ice. There's no question about it, of course. If you don't wait long enough, it stays water. We all know that. But if you leave it in the freezer just right, okay, so the temperature inside for water is below 0 degrees Celsius, but it's still water. It's supercooled water, okay? So if you do it just right, and you take this container out of the freezer, and you pour it into a container, as you can sort of see here. As you pour it down and it strikes the bottom of the vessel, it actually overcomes nucleation barriers, and you have this column of ice forming. So you keep pouring it, and this column of ice keeps forming. So here you have basically all these different phases. So here we have basically a supercooled fluid phase, the actual water falling down. After it strikes the bottom and becomes ice, we have the equilibrium crystalline phase. Okay, it transforms from one to the other. Now, one of the problems that we have, and apart from sociology, is in general, if you think of the common view is that there are lots of competing minima, and you can get stuck in these minima for a very, very long amount of time. It's very hard to get from one minimum to another minimum, from one value to another value, and that underlies why dynamics can become so slow at low temperature. And this way of thinking about it, which is pioneered by Goldstein again 60 years ago by now, is not only, of course, for supercooled fluids, it's also for maybe for proteins, thinking about funnels and proteins and so on. Many computational problems, of course, you can get stuck in wrong minima of those. It's a very general and powerful concept. Okay. And here is again a cartoon of that. Here on the left and the right, there are different problems that you can think about. But of course, as I mentioned, it appears across the board in optimization problems, spin glass problems, machine learning problems, and so on. Okay. Now, what do we know about supercooled fluids and in general, long-lived steady states, which are out of equilibrium? We know what these words actually mean. By which I'm referring to is that if I look at a local observer, I measure something locally. I have a local probe, and I measure what I can measure experimentally with that local probe. I see that actually, as far as I can tell, the system reaches steady state. So basically, I measure it now, I measure it a bit later, it doesn't change. Okay, so, and the system stays in that state for a very long amount of time. Okay, that amount of time is what I call here a tau. It's the lifetime of the state. Ultimately, if I wait long enough, the system will go to true equilibrium. The conventional, so the supercooled fluid will actually crystallize and so on. But that time can be very long, especially by comparison to microscopic timescales. Okay, so here is a cartoon of real data. Okay, so here you can sort of see temperature on the vertical axis. You can see time on the horizontal axis. This is sometimes called the TTT curve, the temperature time transition curve, okay, diagram. So you can see here different phases, and you can sort of see that if you're at high temperature, you're in the liquid phase. Obviously, we all know that. If you can actually cool down rapidly enough and go below the last temperature, you go into a glassy state that happens at the very, very bottom. Okay. If you wait long enough, this is what you see there in orange, you can actually go to a crystalline state. It crystallizes. But you see this hatched region. In this hatched region, the system is supercooled. But basically, if I measure what happens now, I measure what happens a bit later and so on, throughout that interval, the system displays, as far as you can actually measure with local probes, properties that look essentially completely stationary. But if you wait long enough, ultimately the system will crystallize. So the time that you actually have to wait before you actually strike the orange region is what I called earlier tau, and that can be the order of minutes, can be order of seconds, can be order of hours, but it's always much, much larger than the microscopic timescales. So what I mean by that, so if you think about the natural timescales that you have in these systems, so they can be, the overall viscosity can become of the order of 10 to the 12 Pascal seconds. It's when people call it the glass by Fiat. Fluctuation times can become of the order of 100 to 1,000 seconds. When that happens, the patience of it, when investigator, graduate student, whatever actually does it, it runs out because you have to wait too long to actually get data, and that's why people christen it a glass. Okay, but you can compare this to the natural timescales that you actually have for the microscopic process. So let me actually show you or remind you, maybe many of you, of course, know this. One of the longest running experiments in history, which is called the pitch tar experiment. Okay, so the idea was that you would take pitch tar, okay, and you invert it, you cut the bottom, and you wait for drops to fall down. Okay. Now, of course, the viscosity of pitch tar is very high. Okay, the droplets do form. There's a long neck that forms, as you can see here, and ultimately they do drop down. Okay, but the number of events that you have is very, very small because the viscosity is so high. And you can see here in the table at the bottom left the events that happened ever since the inception of this experiment of 100 years ago by now. Okay, so not many drops fell down because the viscosity is so high. And this really is a problem when you have high viscosity, long relaxation times. It's really hard to get data. In this case, as it turns out, there were also other problems. Like a camera didn't work. Just when this happened, the camera actually was off. Okay, and there are other problems of this sort. So we actually didn't necessarily always record it in real time. Okay, you can actually go to a website and actually watch these fall down or just not fall down if you're ever bored, and you'll see it's sort of stationary. But the point is that viscosity can become quite large, and it's really hard to get data. This is one of the, again, conventional cartoons of real data, what happens. Again, on the y-axis is the viscosity in the logarithmic scale, again, because it changes by order of magnitude. On the horizontal axis is the lateral temperature, with temperature at which viscosity becomes 10 to the 12 Pascal seconds, divided by temperature itself, okay? As you can see, all the data are pegged at one point on the right, the top right. That's because by Fiat, you define the temperature Tg, relative temperature, to be that in which the viscosity is 10 to the 12 Pascal seconds, so it has to actually coincide there. But how it approaches that point can vary radically from one fluid to another, okay? And you see some systems actually exhibit a very, very sharp increase in viscosity over a narrow temperature range. These are called fragile glass formers. Some systems are almost completely straight lines, almost conventional activated behavior. These are called strong glass formers. The name does not necessarily matter that much, but there's a big change. Overall, there's a big range of behaviors that you can actually have. This is, again a classical description of what happens. This is, again, from a paper from over 30 years ago by now, by Angel. Actually, I think he was here in Arizona. So he was compiling this a very long time ago, and he had many remarkable results also. The common fit for describing these systems, which I actually don't agree with, but that's beside the point. Most people think it's right, and probably very right. Unfortunately for me, they're probably right, is to think about the Vogel-Folter form. Okay, so the common fit people think about, as I mentioned already in passing earlier, is that the viscosity has an essential singularity as a function of temperature. So viscosity, eta, okay, the top equation that you see here, I hope I can, is a function of temperature, is basically, I'm not sure why it does, sorry about this. It's basically a constant times e to the power, never constant, T temperature minus T0. So if you believe this form, then at temperature T is equal to T0, T naught, the viscosity truly diverges. And most people believe this form, and they take this as as what really happens. And And if this is what really happens, that must be something remarkable happening at t is equal to t0. And this is quite often referred to as relates to the Kalsman paradox. Not exactly the same thing, but relates to that. And the ideal glass transition. So this temperature marks an ideal transition into glassy form. Okay. There have been other works, more recent ones, not that recent by now, but by Parisian co-workers thinking about DMFT approaches. There are also lots of works by Wellness and co-workers, Timolai and Kirkpatrick, trying to derive it using RHOFT. Lots of approaches, most of them actually give or try to give rise to this. Okay. It doesn't necessarily actually work very well in real data, but it's not bad. Okay, so now if you look at the structure that you have of these systems, as I mentioned earlier, they're certainly not crystalline. Okay, so you don't have motifs that appear forever in the system, but locally you do see motifs, okay, like what you see here for silicates and so on. So you do see that you have certain motifs which correspond to what structures that are of low energy. These same motifs also have analogies in spin systems. Many of you that are working in spin systems, like spin ices and so on. Actually, Philip Anselm was thinking about these connections many, many years ago as well. Okay, and these sort of units are what you actually have also in water ice. Okay, I mean, if you want to think about these tetrahedral type units and so on. If you look at real data, which is more complicated, I mean, not necessarily silicates, but actual data, not simulations, and you try to tease out from the data what structure you have. So people actually do is what is called reverse Monte Carlo. So you have experiments, you measure the structure factor and other things, and then you try to find structures that will reproduce what you actually measure. So you reverse Monte Carlo to get the actual thing that you measure. It's much machine learning, but this was introduced many, many years ago, okay? So this are structures that you actually find in supercooled fluids. You see that you have these extended structures that have different types of locally crystalline structures. So BCC-like, FCC-like, liquid-like, and so on. And they can span quite a few atoms. And indeed, if you do simulations, quite generally, you will see that you have regions in which you have clustering forming, which are like locally crystalline structures, and then you have regions which are not crystalline. So we basically nucleate and dissociate, and you keep doing this for a very, very long amount of time, and ultimately the whole system crystallizes, but after a very, very long amount of time. So you can try to find structures in these systems. This is something I did 15 years ago or more by now using machine learning. Okay, this is not, maybe I shouldn't really go over this now because I don't want to go over time. But the question I really want to ask is the following. All of these systems, these supercooled systems, are described by a disorder-free Hamiltonian. So quite often people think about supercooled systems as described, and glasses in general, as described by disordered systems, by disordered Hamiltonians. The couplings are non-uniform, that's what defines big glasses, and things like that. But in reality, the very, very system that would have crystallized, described by the same Hamiltonian describing crystalline state, becomes a supercooled system and glass at low enough temperatures. It's not described by some random looking Hamiltonian with disordered coupling Johnson distribution. It's actually a Hamiltonian of a conventional type, having Coulomb interaction, kinetic terms, and so on. There's no disorder whatsoever in the Hamiltonian itself. Nonetheless, structure-based forms are not necessarily that trivial. So can you relate what happened in equilibrium, described by the same Hamiltonian, to what happens out of equilibrium, but described by the same Hamiltonian? That's really the origin of the distributions of temperatures and state variables that we have. Because ultimately, it's a very, very same Hamiltonian, okay? And the answer is yes, as I already told you, and this, the collapse I showed you, okay? And here, I want to emphasize this point. The only temperature scale in the problem is that of equilibrium melting. So the system, if it's cooled down slowly, would crystallize temperature T liquidus, okay? There's no temperature T0 or T mode coupling or something, or T star or TA. Different people have given different names and so on. It's basically just the empirical melting temperature itself. I already showed you this. Now let me just, in the remaining minutes I have left, let me try to explain to you why we had this particular way of thinking about it. So let's think about the microscopic Hamiltonian. Here I write it down in the quantum formal way, but of course you can do it classically. Nothing special about quantum here. I can write down the Hamiltonian describing the system. There's no disorder whatsoever. What do I have? I have usual kinetic terms for the nuclei, for the electrons, whatever I want to think about, of Coulomb interactions, of course, between electrons and nuclei, from the nuclei, usual stuff. Maybe spin orbit, who knows? But there's no disorder whatsoever in the system. And this system, of course, has eigenstates, obviously. The eigenstates don't look like this, not harmonic oscillator, obviously. Eigenstates are very, very dense, and they become more dense as you go to high temperatures. It's a complicated spectrum, okay? Especially ones that are not solvable. Of course, you have all these Wigner-Dyson type distributions and so on. It's a really complicated spectrum, okay? But the point is that if you actually look at an average over these eigenstates over some window, you basically get what happens in equilibrium. Because as you know, so we have the eigenstates, okay? Of course, you all know this. But the point is that if you were to go and look at what happens, just to give you the idea itself, because I'm running out of time, if I were to do an average over eigenstates in some narrow window of energies, it would give me what I have in equilibrium. This is, of course, what you have macrocanonical ensemble. Macrocanonical ensemble, you basically average over some energy window. Whatever you get in over this average is supposed to describe for a closed system the thermal state at constant energy, and number of particles and volume and so on. Okay, so, but now we cannot have a narrow distribution because if we do have a narrow distribution, we would get the usual Coulomb results, but we don't. So one way out is to say that what you have are states which are special, but are not eigenstates, that don't behave, that don't display the usual hallmarks of what you would have for the average state, which describes a macrodynamical ensemble, which you actually measure in equilibrium. That's one way of doing it. Another way of doing it is to say that basically what you average over is not a narrow distribution, for which you would produce macrocanonical ensemble results, nor a canonical distribution for which you have a width whose scales is 1/squared of n and so on for energy density, but rather something which is wide. So overall, you have a wide distribution of energies or effective temperatures. And that's the only way you can actually bypass, if you don't allow for special states that are different from what you have from macrocanonical ensemble, which you only go to those states and so on. That would allow you to bypass equilibrium behavior. Of course, in reality, all these behaviors are transient. You can argue that in reality, what happens is you measure states in phase space and so on, corresponding quantum analog of that, which are different, and you cannot think about eigenstates because the transition between the different eigenstates is much more complicated and so on. But let's think about what happened at really, really long times, because in reality, the lifetime of these states can be order of 10 to the 17 times larger than what you have for microscopic timescales. So, and a nice thing about eigenstates, as you all know, they're complete. So if I have a Hamiltonian, and no matter how complicated the Hamiltonian is, or how simple it is, it doesn't matter how uniform or disordered the state that I'm looking at is, because the eigenstates are complete, I can always express any eigenstate, any state that I look at, I apologize, within this eigenspace of the Hamiltonian. I can always write down as a combination of these different eigenstates. So no matter how disordered it looks, I can always expand that state in terms of what I would have for eigenstates because of the completeness of eigenstates. Now, of course, this is not new. You all know this. And here are some results that people, including some of my friends, but of course, many others, have for thinking about distributions which are not uniform. So here are calculations done by my high-energy colleagues, thinking about QCD and Miles Verhoef, thinking about states that are non-uniform. Okay, that's what you see here on the left. Okay, that's real space. On the right-hand side, you see things which are much easier to look at. That's the Fourier transform. So if you go to the right eigenbasis, in this case, Fourier basis, diagonalizes interaction. This is essentially a single particle problem, simple field theory. Then in this situation, things are very transparent, okay? This can also appear in real data, but which should be not simulation data. You can look at STM images like this. This is from Seamus Davis's group. Those of you who know Seamus Davis, one of the experts in STM. And it looks like, as he describes himself, like junk, okay, on the left-hand side. But if you Fourier transform, you see very, very nice patterns. So of course, you can go to from real space to momentum space. Momentum space is a complete basis for describing whatever you have in real space for a single particle, of course. But you can do the same thing also for many body states. So in general, as I mentioned, if you use the definition of macrocanonical averages for any observable O with an energy E, by definition, It's the average of excitation value of O over all eigenstates or microstates in the window of finite width. That's, of course, the definition. If a system is equilibrium, it doesn't have anomalous long-range interactions. It's a usual system, the ones that we usually deal with, okay, what describes real materials. This average is supposed to be what you actually measure. Okay, so the eigenstates in equilibrium, their averages over them over some narrow energy window describe what you actually measure in equilibrium. So it tells you something about average energies that was described earlier. So in general, that means that if you go to high energy densities, okay, these states should be describing fluid-like states because the average over those states describes the equilibrium fluid. These states here should describe the solid-like states because the average over those describes the equilibrium solid. You can have a coexistence regime, okay? And in general, if you have some width of distribution of effective temperatures and so on, have potentials, you basically weigh these different equilibrium states, okay? And that's essentially what could happen. So I probably have only 5 minutes left. I don't want to talk too quickly because it, of course, defeats the purpose. Okay, so that's really the point. The point is that these states, from a complete basis, you can use these states. And if you do that and don't have necessarily delta functions in energy density and smaller quantities, then you can reproduce what actually is seen. Now, I mentioned by now, already maybe 4 times, difference in timescales. I said it's very long relative to macroscopic timescales. And so what do I really mean by that? So as I mentioned earlier, this timescale that you actually have for crystallization can become quite large. Okay, so it can go from of order of 3 hours, okay, so 10 to the 4th seconds, for instance, to maybe thousands of a second, but relative to a microscopic timescale, okay, so how long does a collision time actually take? This can become really, really long. Okay, so the timescale for crystallization relative to microscopic timescales can vary between 10 to the 17 to 10 to the 13 or 10 to the 10. Okay, so in this case, if we really take this limit, this to be strictly the limit in which the timescale of crystallization is infinite, then you really must have the distribution I mentioned earlier. Basically, what you actually measure, if it was truly stationary, could be nothing else than what you have in equilibrium with some weights. And the only unknown would be these distributions for temperatures and chemical potentials and so on, all quantities that you usually have as state variables, including any other angles of motion that you might have for a problem at hand. And these distributions P would not be a delta function, because if they were a delta function, it would give rise to the usual equilibrium behavior, but there must be something else. And if you try to see what they could be by maximizing channel entropy, you basically get gamma functions. And that basically is what you indeed measure. So I showed you earlier, we did measurements of the velocity distributions. We inverted that to find distribution of velocities because of distribution of temperatures, because for each temperature, we have a maximum distribution of velocities. And that actually coincided with this distribution that we had for maximizing entropy. And this one is indeed what actually gave rise to the viscosity fit I showed you at the very beginning. So basically, the fit essentially would be of this, if you take the limit of small values of a bar, which is indeed what happens, you have basically Gaussian, and you can evaluate these quantities, you can calculate the viscosity. The viscosity, as you might know, the old-fashioned way of measuring viscosity, of course, you can use, as you might know, many of you might know, Green-Kubo relations, things like that. But the way to measure it in an old-fashioned way is you take a bucket, you take a sphere, you drop it into the sphere into a bucket, you measure the long-time velocity that you have of this dropping down. The terminal velocity of that sphere of a droplet, whatever you were looking at, determines the viscosity. So viscosity is given by the inverse of the terminal velocity. So you have this sphere falling down, okay? This is a raindrop on the left, this is a sphere on the right, and so on. It experiences overall some viscous forces, which is a steady state. You can counterbalance the forces of gravity that you have, viscous forces. You can determine from that what you would have for viscosity itself, and the terminal velocity is equal to constants, okay, times involving also the radius of the sphere and so on, the acceleration of free fall g, and viscosity itself. Okay, so basically you can calculate the terminal velocity that you would have in these when you have these distributions and evaluate that, and from that infer viscosity. So if you have distribution which is basically the type I showed you, a gamma distribution or essentially a Gaussian, you can evaluate the integrals quite readily. Okay, and then you can evaluate what this hardness and what gives rise to these fits. So that's essentially the story. The story is essentially that why can't we think about distributions of temperatures? Also, one of you thought about what and other state variables. Can we actually make predictions from that? How do they actually compare to experiment? If you do simulations, can you extract such distributions? And do you conform to what you're actually measuring? And it seems to be consistent. What I've not shown you, and I don't want to go over time and talk so quickly, which I already am, is how you can actually derive this rigorously, how you can actually prove that if you have an infinitely long-lived state, it must be, there's nothing else possible. It must be essentially a superposition of equilibrium state. Basically, the convex hull of equilibrium states spans stationary states. So that's the story, basically.